Hello everyone. In this video we're going to start talking about lesson 6, which is an introduction to inference. So usually statistics courses are broken up into two different parts. The first part is or talks about descriptive statistics, and so that's the part that we've done so far, and now we're transitioning into the second part, which is inferential statistics. So let's start off, as we always do, with some terms. And so the first term, which is what I just mentioned before, inferential statistics. Now, inferential statistics is the part of statistics where we try to make statements about a given population using the sample we obtain. And so this part, the part that we learn here, is the part that usually you see in the world around you, and it's what you might use later on in your endeavors in whatever major or place that you go, or whatever job that you use. If you use statistics, you'll often use this part. Now, that's not to say that you won't use the descriptive parts. You actually see those a lot more than the inferential parts, but this is what people usually term statistics. Okay, so it's the part of the statistics where we try to make statements about a population using the sample we obtain. So here are some examples of questions that we might be asking, or that might be asked of us, in which we would use inferential statistics. And so I'm going to list off a bunch of them, and they're just sort of food for thought about what kind of questions we might ask. So I could ask, what percent of Americans go to the beach? All of these questions are going to be very hard to answer because they involve a large number of people. And so, of course, it's infeasible to sample all of the people. We can't talk to all of the people. We can, though, talk to a small subset of them. And the question is, how do we go from the numbers that we get from that small sample to making statements about the whole population? That's a very hard step, okay? But it's one we're going to start to tackle here. So what percent of Americans go to the beach? What percent of college students don't like statistics? Okay, and that's always going up all the time, especially in this class probably. It's okay, my jokes are bad, but I'm not there to hear you cringe. What is the mean height of corgis in the United States? Are flipped classrooms effective? When do you have the highest GPA in college? Or which sunscreen is most effective? All of these questions are kind of hard to answer, but we can with statistics. We aren't going to answer all of these questions in this class, but they're questions nonetheless. Okay, so as a motivating example, I want to go through this just to get you thinking about what we're going to tackle in this lesson. So suppose the Coca-Cola company was running a bottle cap promotion this past summer, okay? And what they claim is that 25% of bottles are winners. So you you buy a Coke, and then you look at the cap, and it says winner or not in some sense, okay? Over the summer, I bought 50 bottles, okay, and only won 9 times. So, of course, I'm not very happy because I don't think I won like what I should have won. So maybe I'm mad at the Coca-Cola company. So the question I'm asking is, am I just unlucky, or is the Coca-Cola company lying when they say 25%? And of course, I think it's less than 25%. So how can I go about trying to test that claim? So I have, there are a lot of Coca-Cola bottles that were produced over the time of that bottle cap promotion. I certainly can't get a hold of all of them and see what percent are winners. Of course, I'd love to, but I can't. And so what I want to do is use those 50 bottles that I have, okay, my sample, to see if I can say definitively, or at least with some certainty, that I was being cheated, or was I just unlucky? Okay, and so these are questions that I want you to think about as I go through them. Okay, so first, what are some numbers associated with this? So first you want to think, well, what was the proportion of times that I won? I said 9 out of 50. What is 9 out of 50? Well, it's 0.18 or 18% of the time. So they said that I would win, or that they claim that 25% of all bottles are winners, okay? The proportion that I got, I only won 18% of the time. So, is the Coca-Cola company lying? Okay, that's the overall question. So my proportion was 0.18. The expected proportion, okay, or if they say 25% of the time, what would be the actual number of times that I won out of 50 that would make 25%? And so the expected number of times that I think I should win, if they say 25%, is 12 and a half. Okay, 12 and a half. So maybe 13 times would be what I expected. So is 9 far enough away from 13 to make me start to doubt the claim that the Coca-Cola company was making? All right. So the question is, they're different. 0.18 is not 0.25. Is that enough evidence to say they're lying? Okay, so think about that for a second. Of course, we could have a lively class discussion if we were in class, but in person, but we're not. So you have to think a little bit for yourself. And so another question that might help you with this is, if I get another 50 bottles, okay, I go out, I get another 50 bottles during that time. So if I sample another 50, what will the outcome be? Do I know what the outcome will be? Are they going to be same? Are they going to be the same? Am I going to get 9 again, or am I going to get something else? Hopefully you should think, well, I'm going to get something else. Okay? Not every time, so you're not going to get 9 every time. Sometimes you're going to get, well, who knows what you're going to get, but you could get 10, you could get 12, you could get 15, you could even get 20, maybe even 30 or 40. Okay? So I don't know what they are. But the question is, are those outcomes completely random, or is there some pattern to them? Another way to ask that question is, would one outcome be more surprising than the other? Again, think about that. Your answer should be yes. Okay? So if they claim that 25% of the bottles are winners, and you somehow win 30 out of 50 times, that would be 60% of the time, you should be awfully surprised, right? Okay? 60% is a lot different than 25%. Okay? The same way, if you won 1 out of 50 times, that's very different than 25%. So then, so what I'm hoping is that your perception of the question is changing over time. So maybe first, when I asked you, is that enough evidence to say that they're lying, just looking at the proportions, you might have said, well, yeah, because 18% is pretty different than 25%. But maybe you're starting to doubt that. Maybe that's probably not enough evidence. Okay, just the distance between your proportion and what the company says. That might not be enough. Okay? And so the question that I'm trying to get to is, how can I describe the randomness of the selection process? And what I mean by that is, every time I get 50 bottles, it's unlikely that I get the same number. Sometimes I'm going to get 9. Sometimes I'm going to get 13. Sometimes I'm going to get 15. Okay? Or any number between 0 and 50. Okay? How do I describe that randomness of each time that I get 50 bottles? Right? That's what we're going to discover in this class. Now, hopefully that wasn't completely confusing, but if it is, it's okay. Okay? We're going to get to the specifics later on. I'm just trying to get you to think. Now, how we describe the randomness of the selection process that I mentioned just previously is with something called a sampling distribution. Okay? And this idea of a sampling distribution is going to be central to what we do in the rest of the course. So if there's something that you really try to understand, that you really take the time to think about, it should be a sampling distribution. Now, what the heck does a sampling distribution mean? Well, our goal here is to understand how the random process that we're looking at, okay, in the last example, it would have been selecting those 50 bottles, okay. I don't know before I select them whether a winner or not, so they're random, okay. That's our random process, selecting those 50 bottles. How do they behave under normal operating conditions? And I'll talk a little bit about what I mean by that after. So here's another example to try to get you to think about what's going on. So if I flip a coin 10 times, a fair coin, if I flip a fair coin 10 times, how many times will it land heads? Okay, think about that. And even if you have a coin with you, you can flip the coin 10 times, see how many heads there are. Then flip the coin again 10 times, see how many heads there are. Okay? So do that if you want. If not, just think about flipping a coin 10 times in your head. How many are going to land heads? The answer is, well, it depends, right? If you do it a bunch of times, you should see that it isn't the same every time, okay? But there is a pattern there. Okay, there is a pattern there. So I'm going to show you an applet here in just a second that simulates flipping a coin a bunch of times, and then we're going to see how the outcomes behave. Okay, or see how the heads behave. Okay, so I'm going to. Right? If you click on the link, this is where it will bring you. And so you have a bunch of options over here. We're only going to worry about the top. So I've got a fair coin. Okay, I'm trying to flip a fair coin 10 times. And so if a coin is fair, then the probability of landing heads is going to be 50% or 0.5. Okay, and I want to flip the coin 10 times. And so let's do it. So they have an animated process here. So I'm going to flip the coin 10 times. And so they flip it a bunch. Okay, so it turns out in those 10 flips, I got 7 heads and 3 tails. And so if you look down here, maybe I'll make this a bit larger. If you look down here on the graph, they put a dot at 7. So this is a dot plot, okay, that we talked about before. They put a dot at 7. And so if I flip the coin again, it turns out it was 7 heads and 3 tails again. Okay, and so they put another dot at 7. Now I'm going to turn off the animate feature, and I'm going to flip, do these 10 flips a bunch of times. So as you see, when I click here, that the dots are going up. Okay, I'll do this 100 times, and then we can look at what happened. Okay, so there were 100 flips of the coin, and so if you look at this dot plot down here, you'll see hopefully something interesting. So out of the outcomes I did see, I saw all the way from 1 head and 9 tails to 9 heads and 1 tail. So we saw a lot of different outcomes, but some were more popular than others, and that should make some sense to you, okay? Because it would be very surprising to see a fair coin flipped and get 1 head and 9 tails, or 10 tails and 0 heads. Okay, that would be unlikely to happen, but it does happen sometimes. And so you see here that 6 was happened most often, okay, and then 5 and 7, then 4, then 3, then lower on the tails. So what we're doing here is we're building up a distribution, okay, and so we're going to see. I'll change this, and instead of just 1 time, I'll simultaneously flip the coin 10 times for 10,000 times, okay? And when I do that, I get this plot, okay? And so you'll see at this point of the video, you might be wondering, well, shouldn't it be that the most likely, or the one that happens most often, is that I get 5 heads and 5 tails, because that's what I would expect of a fair coin, 5 heads and 5 tails. And so you see that after I flip the coin 10,000 times, flip the coin 10 times, then did that 10,000 times, that 5 is the most likely outcome. Okay, then it turns to 4 and 6, then 5 and 7, then 2 and 8, 1 and 9, and then 0 and 10 are not very likely at all. Okay, and so we've built up a probability distribution, which we talked about in lesson 4. Okay, it's the mathematical model that we use to describe a situation. And so here you see that a coin flip can be also described by a mathematical model. And in fact, it's described by the one that we talked about. If you look at this dot plot, you'll see that the distribution looks bell-shaped, okay? It's symmetrical around 5, okay? And if I drew a line or a curve through the tops of all of those dots, I'd get what looks like a normal distribution. And it turns out that, yes, this process is governed by a normal distribution. So let's go back quickly to our slides. All right. Here is a histogram of the something similar to what we did. Okay, and so you'll see that it looks very normal. And so that is a sampling distribution. Okay, it describes how the random process behaves. Okay, we have to have special random processes, but it describes how the random process behaves. Okay, so here's the first your turn. I want you to look at that coin tossing applet further. And so I give some directions here. I ask you to keep the sample size the same and then change the probabilities of heads here. Okay, and then I ask you to keep the probability of success the same, and then do different sample sizes. Okay, and then try to answer these questions. All right, so that's where I end this video, and We'll be back next time to keep on going through sampling distributions.